Can you go back into your elementary school time and come up with something in elementary school? I just walked out of elementary school, so I have ideas in my head. But do you think of anything that you've done? How about in your lab sciences here? Because y'all, in order to be in a master's program, you had to have gone through some kind of lab science in your bachelor's. What did you do that might have been experimental? Can you think of something? That's too far back. Really? You're supposed to be able to pull those things out of the back of your brain. All right.
I'm recreation, so I never did a lab science, but I'm just thinking, like, harder work, you get better grades.
Okay.
Cause and effect. So I know that wasn't a science experiment I did.
But you know, people have actually studied that. They've looked at how much time does somebody spend studying. Can they actually track how much time they spend studying, and look at some different factors with that, and then look at what the grade is at the end of the time. Some people look at it and go, you know, how many absences are in a class, and then look at that in terms of its impact on the grade. So a lot of times they just look at a relationship. So if you come to class, you should typically have higher grades. Unless you did what my undergrads did this morning, is they came to class and most of them were sleeping. So it's kind of hard to take it in through osmosis. We were talking about experimental designs just like we're doing here. And I realize it's not something that sounds like really super exciting. However, it's really interesting how experimental design is impacting everything you do right now. So when George W. Bush was in office, there was a huge push to make all of education experimentally designed. So if we were going to put in a new pedagogy, meaning how we teach you how to learn, if we were going to put that strategy in, we had to actually do an experimental design and then publish it to prove that it was okay to put in this new curriculum or to put in a new pedagogical strategy. And so the argument was that in education, we should make no changes unless we actually do an experimental design to see if that works. So you all came through your education careers with that kind of influence in the mix. And it wasn't until Obama came in that things kind of changed and put in a different education secretary so we don't have so much going on with experimental designs. But your whole educational career was influenced by, we have to do studies to see whether we can impact your learning and as to whether we should put it in place. So it does impact what you do directly. But experimental designs actually impact a lot of what you do when you are looking at being an athletic trainer. Because what you have to think about, for those of you going into training, is you learn techniques, right? So you go out and you learn these techniques. Well, who says those techniques work? Just because somebody showed you how to do it? I mean, I would wager a bet that the training that athletic training that I went through in the 1970s is not a whole lot different than the athletic training you're going through today. I would say that a lot of the strategies that you use are the same. Because I spent a lot of time in rehab, myself and with other members of my family, and I'm working with physical therapists doing a lot of the same techniques, and a lot of sports medicine people doing the same techniques. But where there's differences might be in taping techniques. So in some of the things that you're doing today, it might be taping techniques. So there's ways that I learned how to tape that may not be as good as taping techniques today. Or there may be taping techniques today that aren't as good as before. But you should be reading about those and looking and seeing whether there was an experimental design done to see whether those really were effective techniques. Today, and I don't know what those instruments are called. What are those metal instruments that they use that they like? Say it again? Graston. Okay. So they like work your body over. And I have bruises in my hip to show how hard those things are to kind of break down some of the tissue. But they work. There was some research out there that's experimental, says it actually works. If you paid attention to the Olympics and you watched the swimmers, what was the technique that when you looked at, we could never, for the longest time we were trying to figure out, why do all the swimmers have these like circular hickeys on their shoulders and their arms, right? So what were those things? Okay, so that's a cupping technique, right? So do we just like, somebody says it works and so we do it? Or is there an experimental design that's been put in place that says it actually works? I don't know. I have no idea. Have you guys ever looked? Have you ever like seen what it does?
It's like ancient Chinese.
It is. It's like ancient Chinese medicine. That's what I was told. It was, Mark said, well, everybody knows that. It's ancient Chinese. Like, my husband, who's a high voltage lineman, tells me, everybody knows this. Well, this person didn't know. But the question is, even if it's ancient Chinese, does it really work, or is it just ancient Chinese folklore that we think works, right? So what you have to do is you have to look at the studies that you are, you got to look for those studies. And so you really need to look underneath the techniques of things you do to see, is there research that really backs it up? Or are you just jumping on the latest bandwagon? And I'll give you an example of the latest bandwagon that was during my time. So when you work with animals, you can use, what's this stuff that you put on animals to bring swelling down? DMSO. So you can use DMSO on animals, and you put it on, it brings the swelling down. And so they were using it with horses and so forth. When I went through athletic training back in the 70s, nobody ever paid attention to whether there was research supporting that we should use it on human beings. But if you went into the training room, people were using DMSO, like if you had an Electronon Bursa that was damaged, you know how it swells out huge? So we put DMSO on, and we put a pad on, and we wrap it up, boom, swelling's gone. Now it comes back again, but we use DMSO to keep the swelling out. We'd paint it on ankles, and we paint it on knees in order to bring the swelling down. Was there any research that supported it? None that I ever read. We don't use it like we used to use it. People still use it because you can smell people. You put DMSO on, it instantaneously tastes like oysters in your mouth, so you know when somebody's using it and it smells like oysters around them. Training rooms smell like oysters. So what I'm saying is that it's important that you all pay attention to the research about the techniques that you're using, because people jump on the bandwagon all the time in our discipline. You do not have to have a degree to do what most of you are going to do, other than if you can be a physical therapist or an athletic trainer. Most of the time you don't have to have a degree. You can just hang your shingle out and go on and get the latest little shingle out there that says that you're certified to go do something, and it's something that has no professional organization that really underlies it with research that supports what's being done. So when we talk about experimental research, it is really important to you understand it as to whether it works or not. So I'm going to talk to you a little bit today about a few designs that we use in experimental research, some of the things that happen with those designs, and then how we can kind of control for some of the things that might affect it. So there's two terms that we need to know. What's an independent variable? What's an independent variable?
Manipulated.
It's the variable we manipulate, okay? So if I'm going to do a treatment of some kind, my treatment is an independent variable. Okay, so if I'm going to do a physical treatment on somebody, or I'm going to put in some kind of latest curriculum, or I'm going to do some kind of latest technique, that particular thing is my independent variable. Okay? So we have a lot of people getting new knees, we have a lot of people getting new hips. They do a lot of experimental studies on those hips and those knees to see which are the best knees, the best hips to put in place. So, and then they look at what's the technique. Should we enter in the hip from the rear? Should we enter from the front? What's the benefit of one over the other? And we have to do those in blind studies so that we are not being biased in the process. The second one is a dependent variable. What's a dependent variable? Okay, so it's a variable that changes. It's the result, right? So typically the dependent variable is the result. If you go out here and you go south of town, you're heading to Lewiston, and you look on the right-hand side, you can see an experimental, University of Idaho experimental field station out there. And there's crops in little small pockets that there are all test plots for wheat of some kind or another. So if you're working in agriculture or if you're working in forestry, they would call it a yield. So the dependent variable is a yield. What is it? If we do X, what does it yield over here? So if I use 50 pounds per acre of fertilizer, or 100 pounds per acre, or 150 pounds per acre of fertilizer, what does that yield me over here? How many more bushels of wheat do I get? And it's not just a question of how many more bushels of wheat do I get, but what's the quality of that wheat? So like this year, we had massive amounts of wheat being harvested. They're still harvesting wheat. There's so much out there. And they started a lot earlier than they normally do. But they aren't getting top dollar. They've gone from a number 1 to a number 4, which is the low end of the spectrum because it has too much protein in it. So in the soft white wheat, you're not supposed to have much protein, I think is how it works. And so they have too much protein in the soft white, which is the winter wheat. So they lose yield there. So there's certain things that they're looking at, probably because we had a really wet, cold kind of time period with the growth, and that affected protein. So when we're looking at something, we have to look at what's causing these things, what's causing the change on the dependent variable versus that independent variable. So out here, when you look at these crop areas, they're adding either a certain kind of seed is out there. We want to see in dry land farming, how does that work? How much will it grow? Or is there something that we're doing in terms of fertilizer, and how does that grow? Okay? But for us, in a discipline that works with disciplines that work with human beings, we don't have as much control, right? If I could lock you in this classroom, and you live in this classroom for a week, oh, we'd all be in trouble, right? But we could lock you in this classroom, we could control everything about what you do. The light, the heat, the food, the exercise, everything about it. We can do that with rats, but we don't typically do that with human beings. But we could really look at, if we manipulate something, how does that impact it? Because you don't go anywhere. You can't interact outside of this room. But human beings don't work that way. There was a study done back in the 90s in Canada. And they took identical twins. And with these identical twins, they wanted to figure out, do they gain and lose weight the same? Do their VO2 maxes, how much oxygen you take in, how much CO2 you roll off for efficiency? Do you get the same as you work the same workloads? Will you both gain them the same or lose it the same? Body composition, everything. So we're looking at all factors of the health-related components of fitness, plus a whole bunch of other things in the process. So for 6 months, these people lived in a warehouse that was converted to this like huge apartment complex. They kept track of how much food they got, how much water they got. They had a group that looked like this. They had a group that looked like this. They put identical twins in the same kind of thing. And so what they found was that as they controlled for everything they could possibly control, just like we had rats in a cage, they had almost a perfect regression line. And if you can remember back from your stats, we have all of those dots. It's our data points. And we're trying to draw a line of best fit here. So if I have like a perfect regression line, like a 1.0 kind of thing here, that's what it would look like, right? I draw a line right straight through the dots. So the dots are close right around that, okay? Well, that's pretty much what happened when they were looking at VO2 and body composition. So what they did is they controlled for their food, they controlled for their exercise, and they had a certain amount that they had to do every day. And then they measured them and they did some multiple measures along the way. And what they found was, if one twin had a really low body composition, the other twin had a really low body composition. If one twin had a really body composition, body fat, if another one had a really high body fat, the other one had a high body fat. And then when they exercised in the same amount of exercise, they would gain or lose that body fat the same. But they could control for the fact that they were eating the same amount of food. They were exercising the same amount. They took in basically the same amount of fluids. So if they could control everything about these humans that are identical twins, they were able to say that if one looked like this, the other looked like this. Gain or lose weight. Gain or lose weight. So same thing with VO2 max. If they were working out on a treadmill, they'd gain or lose it again. But again, it's in a controlled environment. So when we're looking at experimental designs, with human beings, they're kind of hard to do because you don't get the luxury of putting people in a warehouse that's converted and controlling everything about their lives for 6 months. I mean, I don't know how they managed to make this work, but they got people volunteering to do it. So what we're going to do when we talk about experimental research in our area is we have to see in what ways can we control for variables that could impact that dependent variable. Okay, so if I look at this particular, if I look at this right now, I'm going to give you some notations, because I can't find the PowerPoint that has these notations in it. But in your research book, you will have something that looks like this. And in this particular design, this is the most common design that we use in our area. It's called the pre-test, post-test, and it's really easy to figure it out. You have an O for a pre-test, you have an O for a post-test. Each line is a different group. So we have group 1, group 2. So I have a pre-test, a post-test. Then I have R's, and R's means randomized groups design. So randomized. So if I have a design and I draw it out, if I have groups of people and I randomly select you to be in one group or another, one group will have an R, the other group will have an R. So in this class we have 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18. There's 18 of us. If we randomly selected 9 of us to be in one group and 9 to be in another group, one group would be the experimental group. So I'm going to put that as the top line. So the top line is the experimental group. They're getting a treatment, which is this T. They're getting some kind of an intervention, some kind of a treatment, which is the T. You go down to the second line, this is your control group, and your control group does not get that treatment. What is the purpose of having a control group? Why do we even bother wasting our time with a control group? Okay, so why do we need a comparison? Why is it important to have a comparison?
Just to identify, to see if the treatment worked.
Okay, so part of it is to see if a treatment worked. So if I just have a study that looks like this, where I have an O, a T, and an O, and all I have is one group, because there's just one line, each line is a different group, I don't have a comparison group, right? What's a problem with this design right now?
You don't know if it's random chance that you're ending up with the results that you are. That it's just, you don't know what variables are going into it. Like, what might be throwing something off.
Yeah, so you don't know what's out there. You don't know what this group came with to begin with, right? So you're all above average people or you wouldn't be in grad school, right? If I just went out and pulled 15 people off the street, it's going to have a very different look, unless I'm on the university campus. But if I just go downtown and pull 15 people off the street, it's going to have a very different look when I'm measuring something than if I have you all, right? So if I'm measuring certain things and I don't know where, I know where you started, but I don't know if that's normal. I don't know if that's the normal thing in the population. So having a randomness to it at least gives me a basis to say, and having a second group down here, at least gives me some kind of basis. But the key thing is to have this R in place. So again, we get that thing we've talked about before, which is called that bell-shaped curve or that normal distribution. So if I randomize it, I should have highly skilled people, middle-of-the-road people, and low people all in the same mix. Even if I'm choosing people that are on the high end of the spectrum, everybody's not high on everything. On the characteristic, it still may have a normal curve depending on what I'm choosing, okay? So when I'm looking at this particular design, this pre-test, post-test, so pre, post, and I'll just put that up above. Randomized groups, this is random here. It's the most common design. What you want to think about, we talked about, what should we have for the normal sample size? What did we say was a minimum sample size last time I was with you? 30. That's really true of this. So we would need to have an n equals 15 here, and an n equals 15 here. Anything less than that, and it's really hard to show that your experimental design is working, okay? So, when you're looking at this design here, what you're trying to do in your cause and effect is you're trying to say, I'm going to put it on a separate sheet here. I'll make it a little different here. I got an R-O-T-O, R-O-O. And the numbers down here just signify that they're different measures. They're just different observations, okay? So, when I'm looking at this design here, I want to know, in an experimental design, is the change from the pre-test to the post-test, the pre-test to the post-test, because of this treatment? That's my main thing. So my control group gives me a baseline. Because it's randomized, I should have similar characteristics on whatever my measure is in both groups. I'm looking to see, is the change due to the treatment? Okay? So if I have an observation here and here, both groups, I give one a treatment and one not, it should, if it was done properly, look something like this. Okay? So I could end up with, they're both the same basically to begin with. If one gets a treatment, that measure should go up. And the other measure should stay about the same. The only place where it may not is if I'm doing some kind of an educational intervention. So let's say I'm doing something with reading literacy. I can't give some students a treatment for reading literacy and then an absence of it. They can't, not have reading, or I'm going to have trouble, right? So what may happen is I have a group that goes up, but they go up at a different rate, a different magnitude of change is present. So they get something, but if it works right, the new treatment should go up at a higher rate. Okay? If it doesn't, if they both go up the same, it's not worth putting in a new intervention. It costs money to put an intervention in. Okay? All right, so our goal here is to look at this treatment and see, did the treatment cause the change between the pre-test variable and the post-test variable? So did the IV, the independent variable, actually change the dependent variable? And that's what you're looking at. Did this IV here change this DV here? That's what you're trying to make out. But because we're dealing with human beings, and we don't have them in those warehouses, right? We have things that are going to impact this. We have things that are going to impact this treatment. Okay? So these things that could impact the treatment, we call those internal threats to validity. So what's validity? If we just talk about something, we say that's valid or that's not valid. What's validity?
It's just something showing that your study is actually relevant, that it's...
Not so
that
much
you can-
relevant, because I can say a study's relevant, but it may not be valid. Take it a step
It's
further.
representative.
Sort of.
It's
measured what it's designed to measure.
Yeah, it's measuring what it's designed to measure. It's doing what it says it's going to do. Okay? So, if I were to take a particular test and I use a sit-up test, what does a sit-up test measure? We were to say, what was it?
Core strength.
See, I can tell you're a young person, because you use core, and that's like a terminology of this generation. Why do we call it core? What is it really measuring? I mean, yeah, we could throw the term in there, core, because I'm teasing you, but people use the term core, but what are we really measuring?
Muscular endurance.
Okay, so we're measuring muscular endurance, which is, or it could be muscular strength, depending on which sit-up test we do. So we're using it muscular, but what particular muscles are we measuring strength of? Muscular strength. Right? Which particular McDonald's? Which particular abdominals? Tells you I haven't had lunch yet, I'm hungry. What did you say? Rectus abdominis, okay? So we get really specific in what we're measuring here, okay? So when we go to do a setup has to be done in a particular way to actually measure what it says it's going to measure. If I were to measure grip strength, and I'm using a dynamometer, it's that kind that you grab in your hands and you squeeze as hard as you can next to your body, and then you relax, you look at that, either the pounds or kilograms, however it's set up. What am I actually measuring when I do that? What am I measuring? Take your hand hand down there, put it and squeeze as hard as you can. What do you feel when you squeeze like that?
Forearm,
What was that?
your forearm.
Okay, you feel in your forearm, so it's a measure of strength in the muscles in your forearm, okay? What else is it an indirect measure of? Any idea? If you're doing what I'm doing, it should be pretty obvious. What was that?
Grip strength.
Well, it's giving you grips, because you remember your grip strength, your forearm muscles come down and they attach on your digits, right? Some of them come across, some of them are just here. If you grab this as tight as you can grab this and you squeeze, and where else do you feel it? Okay, you feel it in your shoulder, you should feel it someplace else too.
Tricep or biceps.
Well, you got triceps, biceps, but you should also feel it in your chest on that side. So it's an indirect measure of the muscles in your chest. Maybe you don't have any, I don't know. I've been working out these days. I'm doing a lot of upper body because when I went through menopause, it's like somebody sucked all the muscles out of me overnight. It was like I couldn't lift the plates up onto the, and I was like, this is scary. It's weird because hormones have something to do with muscular strength. And if you have to work that much harder, especially as women. So remember that. But there's a lot that you can do when you're going to measure these things. You look at the validity. There's very direct and there's indirect measures that are present in many of these different tests. Okay, so what we're trying to do is we're trying to see on these particular threats. Are we measuring what we think we're measuring? Are we measuring a change between time 1 and time 2 that is because of the treatment and not because of something else? So we want to know, is this actually what we measured? The effect of the treatment and not something else out there, okay? So we can take a bunch of people like me who've gone through menopause, and are we measuring muscular strength, or are we measuring a function of something else, hormones and some other kind of factor in there, okay? So we have to really think about what are the factors that can influence this treatment. So the threats, Dr. Stahl, how do I bring this up for the PowerPoint?
Main page,
Main page,
PC.
PC. Awesome. Send to all. Send to all. Oh, there we go. And then I can go into here. Yay. Thank you. Okay. So we talked about the cause and effect. Okay. Now, what you have to think about with this cause and effect are these two variables have to be related to each other. So if they're not related to begin with, you can't really do an experimental design with them. So what happens is people do studies to begin with and they look at those relationships, okay? They have to be correlated. If you haven't done a study yet on those variables to see if they're even related to each other, you got to do that correlation first. You got to do a study that looks at the correlation. Then you can look at cause and effect, because cause and effect without correlation means absolutely nothing. Absolutely nothing. And I can also tell you, if you don't do your data right, if you don't enter your data in properly, and you're doing a cause and effect study, you could end up with something not being significant that really should be if your data's not put in right and the variables aren't correlated. So Dr. Stahl and I had that happen with a doctoral student this summer. This doc student didn't enter the data in properly into their study. And when you go to do a pre-test and a post-test measure, it gives you the correlation. And there has to be a significant correlation pre to post-test. Or you got a problem with your data in some way. And we looked at it and there was no significant correlation in his data. That was a huge red flag. Because now something is not showing that it's significant, but they're not even related. We went back and said, okay, give us the original data. We want to go back and look at it. And it looks like people did not get matched up with people. So Jennifer did not get matched up with Jennifer's post-test, and Dr. Stahl with Dr. Stahl's post-test, okay? So when that happens, things aren't correlated. So when we're doing a cause and effect study, we have multiple checks to it. They have to be related. The next thing is, when you're looking at it, there has to be, when you're saying that the change happened because of the treatment, you're saying it's because of that independent variable and nothing else, or very little else that you can't account for. Okay? So, now, here's some things just to think about. Whenever you design your study, it has to have a good theoretical framework to it. Meaning, there has to be a basis for building the cause and effect, period. You have to choose the right experimental design. Even though this might be the most common experimental design, it may not be the best experimental design for what you have available to you. So we can do a fairly decent study, not have it randomized, but do one where we have a setup like this, where we have an O, a T, an O, and an O. Two groups, no pretest measure, not randomized, but we can make it look like this, and we have a chance in some studies. So there are some things you can do. It minimizes, since it's not random, there are some things that you would want to do if you can try to get this thing to be a randomized design like that. That would be a better deal. But in some cases you can't. So you have to look at what the limitations are. Once you choose it, you got to choose the right stats. So that's my job when I work with you on your studies, is to help you figure out the right stats for your design. We have to look at what's the proper independent variable. Some people choose the wrong independent variable as their treatment. They're not even thinking really about, can you actually do the treatment that people say they can do, okay? And the right dependent variable. So if you want to measure, let's say you want to measure anxiety, or you want to measure self-esteem or self-efficacy, or moral development, if you don't choose the right test and theory, the right test that matches the theories that you're doing, it's just blown out of the water. So I know there's theories that you use in athletic training. I know there's theories that underlie a lot of the techniques that you do. But if your test does not measure what those theories are, is not based on those theories, it's the inappropriate test to use. Just because you find the test doesn't mean it's the right test. Okay? Then you got to choose the right people. You got to choose the right people for your study. And then you got to interpret the results properly. If you don't interpret them rightly, you're going to end up with some things that don't make any sense. Okay? So, what we're going to look at right now are what we call 9 threats to internal validity. These nine threats are threats that go all the way back to about 1964 with Stanley and Campbell. These are two researchers that designed, looking at human beings and studies experimentally, looked at designs and how can we have a better understanding of whether the treatment actually changed the dependent variable. So what we're looking at are these factors right here, these threats to internal validity, that can affect the treatment, which then affects the result at the end. Okay, so that picture I gave you a minute ago, where you have the O, the T, the O, that T, and I circled it and drew a line down to internal threats, that's what we're talking about right here. So we're going to look at these things and see if we can control for some of them, all right? And I'm going to go back for just a second. There's one other thing. We have the threats to internal validity, and if we can control for all factors, we have a really tight study, we have really strong internal validity. So if I do a study in a lab, I have really tight controls in a laboratory setting. So I can put you in a biomechanics lab or exercise phys lab, something like that. I can really control for everything. I have very strong internal validity because I can control everything. How much water, how much light, how much heat, how much exercise, what your bed's like, anything like that, okay? But that, if you think about it, gives me a really good lab setting, but is that the real world setting? So we have to take and balance things over here with what we call external validity. So external validity is how much can we generalize what we find. So one of the examples that I like to give, I'm trying to think on this campus. Where's the steepest hill on this campus? Is it out here on Line Street, or is that Line Street out here?
Yeah, right
Yeah.
here.
So let's take the steepest hill on this campus. It's not as steep as the steepest hill at WSU. If you've ever been to WSU and there was the old Taco Time at the bottom, it's now a sushi restaurant or something, I don't know, whatever's down there at the bottom of the hill. And you head up to campus, it's a really steep hill. Not quite as steep as this, but it's steep. So let's say I put you in the treadmill, on the treadmill in the lab. And I've got you running on the treadmill. You're just running as fast as you can on this treadmill, okay? And I keep putting the elevation up, I can put the speed up, you gotta stay with it, you gotta go faster, you gotta go faster, faster. You're running as fast as you can on this thing, right? So, in order for you to stay on and not shoot off the end, you gotta keep moving, and to the point where you can't move any farther. That's a VO2 max test. When I was an undergrad in exercise phys, we did those. We had pads out there, so we'd run as far as we could, and then we'd shoot off the end, which was kind of entertaining. But I can control for all of that in the lab. How much? Every 30 seconds, I start increasing that, I increase it 1 mile per hour. I can't do that out here, right? Because what happens when you start running up the hill? You start going slower and slower and slower. You can push yourself, but you may not push yourself like you would on a treadmill. So the results will be slightly different if we're trying to measure VO2 max out here. The only way I can make it go up faster is if I had a blowtorch behind you, right? Forcing you up there with a blowtorch as fast as you could go. So when you're looking at a study, you have to weigh how much do I want to really know that that treatment worked against how much do I apply that to the real world. So you're all in very practical fields. You're going to balance that a little bit. You got to have some threats to internal validity controlled, but you still got to have a little bit out here in terms of the external validity. All right? So when we look at the threats to internal validity, the first one is history. When we look at the threat to history, these are things outside the study that can influence your results. The easiest one to think about is a fitness unit. If I have a new way of getting them engaged and wanting to be motivated to stay physically active, if I don't account for the fact that I have a whole bunch of kids out there playing soccer, the results that I see at the end could be due to the fact that 60% of them are playing soccer, not that my treatment actually was any better than it would have been if I had just done something normal. So what's the best way to control for history, do you think? What could I do to figure that out? What would I do?
You ask them if they're playing soccer and don't include those children.
So I want to do some kind of survey at the front end and ask them on the survey, what kinds of activities you're in? How long do you do them? How frequently? You know, a whole series of questions. Because then what I could do is if I have 60% of them that look like that, I'll put 60%, I'll analyze their data separate from the other 40%. That way I can see how much does it impact people who are really active versus people who are not as active. Okay? So with history, you want to think about what are you measuring and what things could outside of that influence it. Fitness is really easy to see, but you might be doing a study with anxiety and you ended up getting a whole bunch of people that just came from an anxiety seminar someplace, right? Somebody came to campus and they did something. That's going to influence the results of your study. Okay? Maturation. This is something I have to be concerned with every day in my job. So I'm working with kindergarten through 8th graders. I swear they grow overnight. When I stand next to our 8th graders, when I see them in September and I stand next to them in November, I'm looking up at them. Of course, I'm pretty short, but I'm looking up at them. It's amazing how quickly they grow. So with maturation, that's something that can affect a study when you have young people in your study. The difference between the end of Christmas break, the beginning of Christmas break, and the beginning of the new term in January, you oftentimes will see kids grow an inch in there. Sometimes, this year we had 3 kids who grew 4 inches between September and January. What happens? Any of you grown that fast? Grown 2-3 inches in a very short period of time? Any of you that have that happen? This morning I asked that in my class and I had like 6 hands go up and I said, what happened? And they said, we got really awkward really quick, really uncoordinated, because your body hasn't figured out how to keep up with these longer levers and everything. So you can go from people who are really, really got good coordination to really being uncoordinated, and that can affect your results. So with maturation, you do more frequent measurements. So we do measurements in September, we do it in the 1st of November, we go into February, so those are different ways of doing it. A couple of months in there, and that's good. If you go 6 months, 6 months, that's too long when you're working with children. Testing. This is when you're looking at things that you've given a test, and in a very short period you give it again. So if I give a cognitive test and it looks at anxiety or it looks at self-esteem or self-efficacy, you're going to remember those questions, because some of you are going to look at it and go, did I ever feel like such and such? Because they're going to ask you these questions, right? And you're going to look at it and go, well, that's not me, that's not me, that's not me, that's not me. And the next time you see it again, you're going to go, that's not me, that's not me, that's not me. It's a very short window. You're already still remembering what you saw before. You haven't really thought about it within a new context with that treatment in between. So with testing, you want a minimum of a week between when you do the first test and you do the second test when it's cognitive. You can do physical tests more frequently. So you could do a sit-up test, say on Monday, turn around and do a sit-up test on Friday or Thursday, and you don't have the threat to testing because it's a physical test, and they've already learned it, and it's what they need to do physically to make it happen. Instrumentation, this is all about calibration. So making sure that your treadmill, if you're using a treadmill, is your treadmill calibrated? Is it says 1 mile per hour, is it really 1 mile per hour? So here's the funny thing. I told you before I don't really like fitness centers, but because Mark had his knee replaced, we're going to Nancy's Fitness in Potlatch. And it's this building where it's got good equipment in it, but hardly anybody's there during the times that we go. He'll be on a recumbent bike, I'll be on a recumbent bike, and I'm just pedaling like crazy. My feet are just spinning in there, and I'm looking at those RPMs, and the RPMs are getting up to like 82, and I'm burning calories, and I got my distance going, and I get done after 15 minutes, and I go, wow, I just burned 52 calories. And Mark's, he's in there, and he's working. Again, his knee's not working quite as good, but he's got a good clip going. He goes, man, I just burned 150 calories. I'm thinking, he just burned off part of dinner, and I just got a potato chip, right? So we're working about the same. I'm pedaling like crazy. The two machines aren't calibrated. They're not calibrated to each other. So I keep trying to tell him that he really didn't burn off that many calories. And he keeps trying to tell me, well, you really burned off 150. I know better. I didn't burn off 150. But you want to make sure that your machines, whatever you're using, are calibrated the same. If you're doing something with computers, you want to make sure your computers have the same speed to them. You want to make sure that the internet system that you're using has the same amount of speed to it and the same bandwidth, or you're going to have problems. Okay, so everything has to be calibrated. And you have to calibrate it, if you're in an exercise phys lab, temperature and humidity impacts oxygen and CO2 in the air. So if you're in the southeast, you got to calibrate fairly regularly because you have a lot of hot temperatures or cold temperatures with a lot of humidity. Whereas here we're pretty dry. But you have to do it multiple times throughout the day if you're testing all day long. What time am I doing?
Whatever you want to do.
Oh, I don't know when your class is done.
145.
Okay, all right. So statistical regression. This is when you choose people on extremes. So it's not randomized. So think of an example. What would be an example of something where we were measuring people on something that's extreme? What could you choose?
I'm not sure if this classifies, but during undergrad on our mock research study, we would do like VO2 or 1.5 mile run tests and try and compare it to VO2 max, but a lot of our participants were student athletes, and so they had a crazy amount of physical activity per week than the rest of the participants. So that's
Okay.
like it was extreme.
So I'm going to move that one to another so we don't lose that thought, okay? I'm gonna put it in this category here called selection, maturation, interaction. So, we have an interaction between how we selected people and the maturation that's there. So if we only chose athletes, and that's all we chose, and they were cross country, or swimmers, distance swimmers, they're extremes. Okay, so we could use that. But when we have two groups this way, we would talk about the selection, maturation, interaction. And in this case, you have a group that is highly trained, working out like crazy all the time. And then you have the average Joe Blow on the street. So there's a maturation thing that's there in terms of the selection, because those people, and you're going to think this is funny because it's going to be backwards of what you think. Those people who have the massive amounts of exercise, how far are they going to change? How far are they going to change in your study? If you are at the high end, how far do you have to go? Let's say that if you are, for a guy, if a guy is at 60 milliliters per kilogram per minute, that is like really high. We've had people up in the 76 milligrams per kilogram per minute. That would be like the really high end of people, okay? So let's say we have a group of people up there, okay? And then we have a group of people that are about 40 to 45 milliliters per kilogram per minute, which is where I guess most of us would be in here in one form or another, okay? So if we have this high end, how much higher than 76 milligrams per, 76 kilograms per minute could you go, do you think? If you're at 76, where do you think you could go? You guys had exercise phys? What do you think? So in your head, when you do exercise phys, in your head, you should have kind of an idea of where people ballpark, just in general. Just like, if you're an athlete, you look good if you're 50 and above. If you're a non-athlete, you're between 40 and 50, that's pretty good. If you're in the 30s, you're the walking dead. If you're in the 20s, you're definitely dead. You're not taking in much oxygen, right? You need supplement at that point. So if you're up in the 70, 60, 76, you don't have any room to go. You're maxed out at where you can go. You can maintain it up there, but you're maxed out. But if you're in the 40s, you got room to grow. Unless you're getting older and it's really hard to get up that high. But you got room to grow. Okay? So what would happen is your people got room to grow are going to grow the most amount. So that's where you're going to see the increase. And the people who don't aren't going to grow very much. So you're going to say, well, but these are athletes. They should get better than where they are. Well, they've maxed themselves already. Look at where they are to begin with. They don't have much room to grow. But look where these guys are to begin with and see where they go. So the selection, maturation, interaction means that by virtue of the groups you chose and the groups you put them in, one group is going to grow much faster than the other. You can look at the same thing with tennis. If we have the Arthur Ashe Tennis Camp, which is out of Detroit, we can take all the kids that are in Ann Arbor, and they got a tennis court on every corner. They go home and practice all night long. You go into Detroit proper, there's no tennis courts. They don't have anything to practice against. So the kids in Ann Arbor are going to get better quicker than the kids that are in Detroit. So that's a selection, maturation, interaction. You've got to look at, when you don't do them randomly, you got to think about who's going to grow because they have the opportunities, who's not. Okay, so that's that maturation, interaction. So if we come back and we look at statistical regression, if we measure people on an extreme to begin with, so if I measure VO2 max and I get them, let's say, averaging 65 milliliters per kilogram per minute. It's hard to get that out. If I do that, the next time I measure them, they may not be quite that high. The scores come down a little bit. So they regress more towards a more normal mean. So they might be 55, not 60. So you have to be really careful when you choose